In this segment, we'll talk about steps of solving an engineering problem. The reason why it is important to talk about this in a numerical methods course is because the engineering problem solution is obtained by solving some kind of a mathematical model, and many times that mathematical model requires numerical methods. So how do we go about solving engineering problems? So what we basically do is we describe the problem. Then we develop a mathematical model for it, and this might be coming from analysis, this might be coming from experimental data, this might be coming from numerical data. So it can be all sorts of things or a combination of them. And then what we want to do is we want to take that mathematical model and to solve it. And then, of course, the big part is also to take that solution which you just found for the mathematical model and be able to apply it to the solution of the problem. So what we're going to do is we're going to take an example and we'll go through these 4 steps. So the first step is problem description. So here what you are seeing is a drawbridge which you find along the waterways throughout the world. It simply is a first class lever, and it has a fulcrum right there, so it basically opens and closes just like a seesaw. In fact, the Baskerville Bridge name comes from the French word for seesaw. And this is a close review of it when it's being constructed. And what I would like you to pay attention to is the fulcrum right here. And it is not entirely visible there, but the fulcrum is right there of this Baskerville. So this is a close-up. This is a close-up of the Baskerville Bridge fulcrum here, and it consists of 3 components basically. That you have the trunnion, which is simply a hollow or a solid cylinder, and then what you have is that it is put in this item called hub, and then the trunnion hub is put into the girder of the bridge. And that's how this first class lever is made for a drawbridge. So how does the trunnion hub girder assembly procedure work? So here are the 3 components which are shown here. So this is the trunnion, this is the hub, and this is the girder. So what you do first is that you take the trunnion, this one right here, and you immerse it in dry alcohol mixture. Why do you need to do that? Because it won't otherwise go into the hub. So because the outer diameter of the trunnion is bigger than the inner diameter of the hub. So we immerse it in dry alcohol mixture, it contracts the diameter, we shrink fit it into the hub, and then it simply is left to warm up. But it's not finished yet. What you got to do now is that you got to take this trunnion hub assembly and put it in dry alcohol mixture so that the outer diameter of the hub starts to decrease so that it can go into the hole in the girder. And that's what the eventual assembly turns out to be. So what was the issue in doing this trunnion hub girder assembly was that in one of the bridges what happened was that when the trunnion was cooled down, the trunnion is supposed to go all the way up to this point right here into the hub. So this point here has to match this cross section of the hub, but it got stuck halfway through. So we want to figure out why did that happen. So the magnitude of the contraction which is required in the trunnion is was supposed to be 0.015 inches. So you wanted the magnitude of delta D to be greater than or equal to 0.015 inches. So it had to contract more than 0.015 inches. How did we get that number? That number is obtained by knowing what kind of fit was required for the specifications. In this case, it was an FN2 fit, and that required the contraction to be at least 0.015 inches. So what we got to figure out is, hey, did it contract enough? So in order to do that, we have to do mathematical modeling. That is the second step of solving an engineering problem. So this problem was given to a consultant, And what the consultant did was simply said, hey, I know my physics 101, so delta D, which is the change in diameter, will be the diameter multiplied by thermal expansion coefficient of the material, which was cast steel, and multiplied by delta T, which is the change in temperature, because that's what comes from the definition of the thermal expansion coefficient. The coefficient of linear thermal expansion is the change in length per unit temperature. So using that definition right here, we have the diameter. We get our alpha from a handbook. This is the room temperature alpha. The change in temperature is 80 degrees. Let's suppose if we assume it to be the room temperature, minus 1/8 is the temperature of the dry ice and alcohol mixture. So the change in temperature is minus 188 degrees Fahrenheit. So if we apply this formula right here, D is 12.363. The alpha is given to us 6.47 10 to the power minus 6, and the temperature change is minus 188. Multiply the three numbers and you get this number right here. So this, if you look at the magnitude of the contraction, is 0.01504 inches, and it is more than what we wanted. Right? The specification required that the change in the diameter should be more than 0.015 inches, which it turns out the case. So what's the issue here? The issue here is this the correct formula to use in the first place? Delta D is equal to D times alpha times delta T, when you can recognize from literature that alpha, the thermal expansion coefficient, is a function of temperature. And you can see that as the temperature decreases, the thermal expansion coefficient also decreases. So you're not getting the same amount of contraction at every temperature. In fact, as it gets cooler, the amount of contraction which you're getting per unit temperature starts becoming smaller. So if we have to recognize that, is this really the correct formula to use? The correct model would be to account for the varying thermal expansion coefficient. So what that implies is that we'll have to use this formula, is the delta D is equal to D times alpha times delta T. This might work for temperatures not varying too much, so it's an okay formula to use if alpha is not varying a whole lot between the temperatures it is being subjected to, but it is not the right formula to use when thermal expansion coefficient is changing. In fact, you'll find out that this formula does reduce to this formula right here if alpha is a constant. So the next step is solution of mathematical model. Let's go and see how do we go about solving this mathematical model. So the mathematical model which we have is that, hey, the change in the diameter is not given by D times alpha times delta T, but it is given by this integral right here. And now what you are seeing here is that you got data which is not given as a continuous function of temperature. So what that means is that, hey, I cannot simply use my integral calculus knowledge of exact integration to be able to find out what the change in the diameter is, because I got to do this integral first and then multiply it by the diameter. So how do I go about doing that? So let's go and see, can we roughly estimate the contraction? So what we can do is we can say, hey, I was at 80 degrees. That's the alpha 80 degrees. At minus 108, it is this. So I'm going to simply somehow say, hey, let me draw a trapezoid here. And this is 80. This is minus 108. If I'm just doing it rough estimation on the first day of class. So let me see what the area under the curve is. Although the curve is given only at discrete data points, can I find out the area under the curve? So this area under the curve, which you're finding out here, is a trapezoid. So I'm going to say, hey, this one looks about 5 or so, 10 to the power minus 6. That is the height of that parallel side. And the height of this parallel side is about 6.5 times 10 to the power minus 6. Divided by 2, so that gives me the average length of the parallel sides multiplied by the perpendicular distance between the two parallel sides, which is minus 188. So that is the area of a trapezoid, right? average length of the parallel sides multiplied by the perpendicular distance between the two parallel sides. And what I get here is minus 1081 times 10 to the power minus 6. And so if I find my delta D will be 12.363 times minus 1081 times 10 to the power minus 6, and this number here turns out to be 0.013364 inches. And this quantity right here, the magnitude of this number is not bigger than 0.015 inches. So right there we can see that, hey, in fact, actually we did not get enough contraction. Another question which people ask is that, hey, where did I get this minus from? Although the area under the curve right here is above the x-axis, in this case is temperature, but look at this. We are integrating from a higher temperature to lower temperature. We're integrating from right to left, and that's why this integral quantity right here, the area in the curve, is a negative number right here. But what we have shown is that, hey, delta D magnitude is turning out to be less than 0.015 inches in this case. Now, in the previous slide, we talked about how to estimate the contraction with a very rough estimate. Can we do it a little bit more accurately? Yes. What we can do is we can approximate this data which is given to us by a second order polynomial regression model. So these terms which I'm just talking about, polynomial regression model, may not be familiar with you, but later on in the course when we talk about regression, you'll be able to see that, hey, where do we get this from? So at this point, what you got to think about is that, hey, if somebody gives me several data points relating one variable with another, I can get an approximate formula, maybe a second order polynomial, first order polynomial, to approximate the data. So this is what we get to approximate the data, a second order polynomial. But the great thing about it is that we can just simply include it in here in this integral here. And since everybody knows how to integrate a second order polynomial exactly, and we already know what the value of D is, then we can find out what delta D is. So we're getting very close to what we got previously. Even with the rough estimate, we got minus 0.0133, and here we're getting minus 0.0137 inches, and that's still, this magnitude delta D is still less than 0.015 inches, even if we do a more accurate estimate of the change in diameter. So the question is that, hey, although we have been able to answer the question that, hey, why it got stuck, but that's not what real life is looking for. Real life is looking for a solution. Hey, okay, you got a solution to this mathematical model. Can you use this to maybe come up with a solution where it will not get stuck? So here is one way of doing it. So one of the ways of doing that is that, hey, we don't put it into dry ice and alcohol mixture, but what we do is we put in liquid nitrogen. The liquid nitrogen temperature is, boiling temperature is minus 321 degrees Fahrenheit. So by conducting the same exact calculations as we have for dry ice and alcohol mixture, by putting alpha right here and putting the lower limit and upper limit of integration, this is the diameter of the trunnion, we get a delta D of 0.0244 inches. And this delta D right here is greater than 0.015 inches. So what we have done is that we have, first we have used the correct model to show that, hey, delta D, the change in diameter is not enough for it to get, for it to have what's that called, a proper shrink fit. So what we need to do is we need to put it into a cooler medium, and that cooler medium would be, let's suppose, liquid nitrogen. So let's go and revisit the steps to solve an engineering problem. We just solved an engineering problem. Let's go and revisit these steps. So what is the problem description? that the problem description was trunnion got stuck. Now, this is too reductive in nature, but problem description in real life could run into pages. But here, I'm just recalling that, hey, trunnion got stuck. It should have gone into the hub, but it didn't go. What was the mathematical model? We used a mathematical model, which was this, but we recognize that this is the wrong model to use in this case because thermal expansion coefficient is changing over temperature. So the correct model to use is this. And then the solution of the mathematical model, when we did it by using the rough method, we just said, hey, let's do trapezoidal rule, where we just approximated the area of the curve by trapezoidal rule. The more accurate method was to regress to a second order polynomial, right, plus integrate. That's what we did. We said, hey, let's go ahead and find a second order polynomial approximation of the thermal expansion quotient as a function of temperature. Then we can plug it into the integral which we have right here, and we can find out what delta D is. Then how do we use the solution? We use the solution by saying that, hey, let's put it in liquid nitrogen. Rather than putting in triazine alcohol mixture, which did not give us enough contraction, let's go ahead and put in liquid nitrogen where we get enough contraction.